Okay, welcome back. So if you recall, in the last lecture we had concluded MOS capacitor. We have discussed the expression for threshold voltage, and I told you in a real capacitor there will be oxide charges that will play a role, and the threshold voltage will also be affected by the flat band voltage if there is a difference in the work function between the metal and the semiconductor. So we told that from today we shall start MOS transistor, MOSFET, that is field effect transistor. Field effect transistor builds on the basic premise of an MOS capacitor, except that now we shall have a source and a drain. It is a 3-terminal device, and unlike MOS capacitor, which is a 2-terminal device, this is a 3-terminal device. So it will be a little bit more involved, and a transistor is an active device, which means it can have gain, and we have to understand various aspects of this MOS transistor, and we will always recall the expressions and the equations that we had used in MOS capacitor, because those will be used in deriving many of the expressions in MOS transistor also. Okay, please remember that silicon MOS transistors are the most widely used transistors in your integrated chips, processors, memory, logic, and so on. There are different variations of MOSFETs, and nowadays you have very highly scaled 3D versions of MOSFET, but nevertheless the basic MOS transistor we should definitely be familiar in order to understand all the how the modern electronic gadgets work. Okay, so let's come back to the last slide that we had left. If you recall, let me take the laser pointer here. If you recall, this slide had shown you the final equations regarding MOS capacitor. We have to start from here. So if you recall, this is the metal semiconductor work function difference. This is the contribution from the oxide charges, the fixed oxide and the trap charges. So this entire quantity essentially represents the amount of voltage by which your flat band voltage has shifted. Remember, ideally your flat band voltage is 0 if the metal and semiconductor work functions are balanced and there is no interface charges. So this quantity of flat band voltage you have to apply to essentially this quantity, you have to apply this, whatever this voltage comes out to be. You can do a calculation and find out. It may be minus 0.5 volt, it may be plus 0.5 volt, anything, that amount of voltage you have to apply to the gate of an MOS capacitor to make the bands flat. Okay, and this flat band voltage has to be added to this particular expression, this one you see here, this particular expression over here, that is the ideal expression for threshold voltage. When you apply some gate voltage, this is a gate voltage at the threshold, of course. When you apply some gate voltage, part of it falls on the oxide, that is what it means, and part of it falls on the semiconductor, that is what it means. In inversion, in strong inversion, the band bending or the voltage dropped in the semiconductor will be 2 times phi f. Phi f is basically your difference between the intrinsic and Fermi level and the Fermi level. Okay, so you will basically have this expression as the fundamental expression or the ideal expression for threshold voltage. To that you add this particular voltage, flat band voltage, you get the total net expression for threshold voltage for turning on the channel of an MOS capacitor. Okay, and do not mess up the signs of these expressions. For example, Q of S represents the charge stored in the capacitor in the semiconductor, because if we talk about a p-type substrate, then this is the depletion charge, and the depletion of p-type forms negatively charged acceptor ions. So this will be negative for a p channel, for a p substrate MOS. A p substrate MOS gives you n channel transistor, n channel MOS for capacitor, because you invert the channel, which means if you have an n channel device, like the n channel device, that this is an n channel device we are talking about, which is a p type substrate. This is a p type substrate, electrons are formed here, so n channel on a p type substrate. In this kind of case, the depletion charge that is here is basically negatively charged acceptor ions, which means this expression that we have here, let me come back here, this expression that we come here is actually negatively charged, and this negative sign will basically make sure that this entire quantity becomes positive, because minus of something, right? So let's not mess up the charge, the signs of the expressions and the terms. Like this is a positive oxide charge, typically it is a positive oxide charge, so this negative will remain negative. Okay, so let's keep that in mind. So this is all about your MOS capacitor. You might also recall that we had gone through other expressions of debye length and also. Let's not go back there again. Now we'll come to transistor, and how a basic transistor looks like. A basic transistor actually in a MOS capacitor, MOS transistor looks like this. So let's take a minute and understand what it basically means. This part is actually an MOS capacitor. If you look at this part, this is an MOS capacitor. You have a gate oxide here. The DUC is exactly the gate oxide that we have talked about. This is the gate. there is a channel that is formed. So this part is essentially whatever we have learned in the last few lectures. This is the MOS capacitor, except that on the left side now there is an N plus region, N plus very highly doped region. On the right side also you have an N plus highly doped region, and these regions will slightly overlap with the gate. You see below the gate they slightly overlap. So there is a continuity here, in a way. So this is called source and this is called drain. This is a channel that is formed, which is basically the inversion channel that we have learned till now, and this is the oxide, this is the dielectric there. So don't worry about that. So everything looks same, except that now don't worry about this oxide. Okay, this says oxide, that is this isolation sort of a thing. We will not worry about that. You see this is a metal contact on this source. Of course gate also has a metal or a polysilicon or whatever, and source again drain also has a metal, this black colored here. So this is an N plus very highly doped pocket, like a source, and this is also N plus doped highly doped pocket like a drain, and this is p substrate, and the channel is inverting here. As soon as the channel inverts here, when you apply a strong positive gate voltage, your channel forms here, as we have discussed in the last few lectures in a MOS capacitor. This channel will form here because of strong inversion, if you recall. Now this is N plus, this is a high density electron, this is again N plus. So you see from here to here you have a path. N plus source can talk to N plus drain. That means there will be a very high current that goes through this channel of high density electrons that is forming here. Okay, for the current to flow here now you need a field, a drift sort of a equation or a drift kind of a transport, such that the electric field will drive this high density of inversion charge that has formed here, that has to be driven from this point to that point. So electrons have to flow, so current have to come out. So what you do is that this source you ground, which means you apply a zero potential, you apply ground, and on the drain you can apply a higher voltage like plus 2 volt, plus 5 volt, plus 10 volt, whatever, right. So that when you apply a voltage difference between this point drain, say plus 5 volt, and a ground that is 0 volt, so in between them there is this channel that is a high density electron that is formed because your gate is now biased at threshold voltage or more. Okay, so that means because of the field, there is a plus 5 volt or maybe plus 3 volt, there is a 0 volt. So there is a field between source and drain that will lead to a drift sort of an equation or the transport of these electrons that will try to flow from the source. This is like an infinite reservoir of electron, because you are already connecting it to the ground, you are completing the circuit. Your electrons will try to flow so that you will get a current across this channel here. You will get a current across the channel here. Electrons will come out from here, which means current actually is going in here. Okay, that's the convention. And of course, if you apply a little lower gate voltage, that is a voltage that is lower than the threshold voltage, then this channel will not turn on. It may be in weak inversion, it may be in depletion, if you remember. And then if the channel doesn't turn on, then the source and drain cannot talk to each other. I mean, they cannot have current between them, which is what I mean, because this channel has vanished, which means you can turn off this channel. You can turn off this channel by applying a gate voltage which is lower than the threshold voltage. In that case, the current between source and drain will be 0, almost very, very low, even though you apply any arbitrary drain voltage here. This is called drain voltage, this is source voltage, right? This is at 0, this may be at 5 volt. If your gate is lower than threshold voltage, which means your channel is turned off, then no matter how much voltage you apply here, your current between source and drain will be negligibly small. You might apply 5 volt, 10 volt, 20 volt here, but source and drain will be basically an open circuit. There is no channel between them. So the gate is basically controlling, okay, this third terminal over here is controlling the current flow between this first and the second terminal. In other words, the voltage difference between this first and the second terminal, between source and drain, the voltage difference between them and them is actually not playing a role in the current. It is rather the third terminal which has this ability to make the transistor channel vanish or come back. If it applies a gate voltage higher than the threshold voltage, then the channel will come back, the strong inversion will occur and the channel will come back, and you will have a current between the source and drain. The moment you turn off the channel by applying a lower gate voltage, then the channel vanishes and source and drain current also vanishes. So that's why this is called a transistor, where the voltage difference between 2 points is not able to control the current so much. It's basically the third terminal which is able to control the current between the two terminals. Okay, that's why it's called a 3-terminal device. The third terminal is the mega terminal, the main important terminal which controls the current here, and it's called a transistor. Okay, now of course there's a lot of physics behind it, a lot of equations will come. You see, because the source is 0, the drain is at some finite voltage like plus 5 volt, plus 10 volt or whatever. So along this channel the potential will vary along this direction. Suppose this I call the y direction, this is y direction. So the potential will vary along the y direction because this is a higher voltage, this is 0. But recall, in our MOS capacitor we didn't consider this direction y was not important to us. This z also is not important. Basically this is the width of the device or the periphery of the device. You can always normalize the current or whatever the periphery, so this is not an important factor. If you recall, in our MOS capacitor, I'll again quickly show you a figure of an MOS capacitor. You see, this is an MOS capacitor. In this case, all this band bending that is happening, this is happening in this direction, the direction perpendicular to the gate oxide and metal. Okay, it's happening in this direction, the band bending, the inversion formation, the depletion formation, all this equation, all these band diagrams are in this direction. Please remember, in this direction, the direction in which I am moving the laser pointer, this direction is basically the direction perpendicular to the interface of this semiconductor and oxide, or oxide and a metal, and so on. Okay, we don't care about the direction in the direction that is entering the plane of this slide. Okay, not in this direction. So what I mean is that if you come back to this MOS transistor diagram sort of thing that I was showing you, okay, the MOS diagram, this diagram for example, so this is the direction which is perpendicular to the metal semiconductor interface, I mean the oxide semiconductor interface, the metal oxide interface. This is the diagram. Look at the laser pointer direction. This is the direction which is the x direction. This is the direction in which the band was bending, because the gate and the substrate was, we are biasing this in this direction. So the band bending, the inversion, the depletion, everything was happening in this direction. But now there is an additional y direction, which is because this is at 0 potential, this is at maybe plus 5, plus 10, whatever, right? So there is, because of this difference in the potential, along this y direction the potential will keep changing. The potential will keep changing. So basically this whole picture becomes a 2-dimensional in a landscape where you have y direction along which the potential changes because of the drain bias, and along x direction because you are applying a voltage on the gate. This is the direction in which our MOS capacitance analysis was done. So we have the 2-dimensional picture. It's not very easy to solve, so we'll do some approximations and assumptions to make it simplified, okay, into 1 dimension. That is the thing. Now you understand the basic working of an MOS transistor, how this terminal is able to control the current between the source and the drain. Okay, is able to control the current between the source and the drain, and this is a transistor. It can act like a switch in a way that by either taking this gate voltage higher and lower than threshold voltage, you can actually switch the channel on and off. The current between this point and this point will not depend on the voltage between this point and this point, but rather on this voltage. So it's like a switch. You use it, and you can use it all the digital logic that you do, all the NAND NOR gates that enable you to have the digital hardware and the digital electronics. It actually, the NAND gate, the NOT gate, everything works like a, it's a logic gate. I mean it's a switch sort of a thing, because the either you have a 0 or a 1, that depends on whether the channel is on or off respectively, and then you have a gate voltage that you apply that will control essentially whether the state that you're looking at is 0 or 1. Okay, so there's a lot of applications. You can also have a design of the transistor such that if you apply a small signal of an RF here, you might get a very amplified signal here, in which case it will be like an RF amplifier. In some cases it can be like a power switch, where you either have to block a very large voltage and conduct very high current. So there are many kinds of applications of the MOSFET, depends on design and many of the other aspects, but the basic operation is the same everywhere. So we'll first look at, although we have understood how the MOSFET works, we'll also look at the basic IV characteristics, the current voltage characteristics of a MOSFET. How do they look? Okay, how do they look? Now we have to stop back, and we'll pause and look at that very carefully. But before that, of course, we have to look at this particular band diagram that I am drawing to you in a 3-dimension. Actually, if you have to be very careful here. So you look, this is basically the transistor that we had looked here, except that I am flipping it perpendicularly. So this is the source, this is the drain, which is the source and the drain. So remember, this is the depth of the structure. This is the direction, the x direction in which the band bending was occurring in our MOS capacitor studies. So this is the x direction. Remember, this is the x direction. So your band bending will happen in this direction. this is the x direction. Please remember, this is the x direction. So your band bending will happen in this direction, which means if you are applying a gate voltage which is more than the threshold voltage, then your bands will bend here, not here. These are far away from the interface between, this is the gate dielectric semiconductor interface. The inversion charge will happen here, not over there, not over here, it will be here. And the moment you apply a positive voltage on the drain with respect to the source, this band along this direction, along the y direction, along the y direction it will bend, along the y direction it will bend, but also along the x direction it will bend because of this gate voltage to induce a channel. If the gate voltage, as I told you, is lower than the threshold voltage such that the channel is not formed here, then even if you apply a higher drain voltage and even if your band diagram bends like this, you will actually not get a current because your channel inversion has not yet happened. Okay, if your gate voltage is lower than the threshold voltage. So this is a condition that this condition was an equilibrium condition where the gate voltage, drain voltage, source voltage, everything was at 0. Now I'll apply a small gate voltage so that I want to bend and form a small channel over here. So you see this is a small channel that is forming here. You see the difference from here to here. You know, it's bending, and there's a formation of a channel here. This is source, this is drain, and they are both at 0 0, so there cannot be any current between them because it's 0 and 0. There is no field here. Okay, there is no field here, so nothing will push them out. The inversion that has happened here will lead to some electrons at this interface. That is exactly like the MOS capacitor that we have studied till now, except that now we'll have a difference here. We'll apply voltage here. The moment you apply voltage on the drain side, the drain will bend. You see the drain is bending now because you are applying a voltage here, and this total bend that has happened from the source side to the drain side, the total band bending that has happened is actually given by the drain voltage that you are applying. So this entire band that has happened, the amount of this band is essentially equal to the voltage on the drain that you are applying with respect to the source. So you know, there's different Fermi levels and quasi Fermi levels that are shown. You don't have to worry so much. Essentially there's a channel that is formed at this interface. At this interface you have a channel. That interface is here. The channel will basically now conduct current because the source and the drain are at different potential. So electrons will be fed here, they will come back down here and get collected here. The moment you turn off the channel, it will go back to something, you know, this is not a channel turning off, this is the drain voltage being 0. But even if you turn off the channel, the inversion will vanish here. Even if this voltage difference exists, you will not be able to get a current. Okay, so this is the condition when the gate voltage is also, you know, moving towards threshold, and also the drain voltage is higher, is good amount, so that you have a band diagram like this. Now the IV characteristics, the current voltage characteristics of a transistor, which is the most important thing that you need to always remember. We'll come to that step by step, and we'll show you how the transistor characteristics look like. Okay, so first we'll look at the band diagram. So take the situation when your you see, but remember, this is N plus pocket and this is your P type substrate, this is N plus drain pocket, this is a P type substrate. So between N plus and P there will be a depletion region. The depletion region with the depletion which is marked by this dotted, this dashed lines, if you remember here, so you can see here. So there is a depletion that is formed between the N plus source, N plus drain, and the the substrate here. And because these are N plus, the depletion will predominantly extend towards the lightly doped P type substrate. So this entire depletion region is actually towards the lightly doped substrate region. You might say, this depletion I understand, this depletion I understand, why is there depletion below the gate? Well, I am applying a gate voltage which is stronger than the higher than the threshold voltage, which means I have induced a channel here. I have induced a very high density electron channel here because the gate voltage I am applying is more than the threshold voltage. There is no point discussing gate voltage lower than threshold voltage because there is no channel, there will be no current, essentially your channel will be off. So I am applying a gate voltage which is slightly or maybe higher than the threshold voltage. There is a high density of charge here, and if you remember, when you have a charge, whether you have an electron gas density here or not, but the moment you apply gate voltage which is positive, your holes will be repelled away from here. So you will have a depletion region around this part also, and the depletion also forms here, depletion also forms here. Okay, so you will have a depletion throughout, and remember this gate voltage is slightly more than the threshold voltage. Now there is a channel that is formed here. Now the first condition is that I apply a drain voltage here which is much lower than a voltage at which the current saturates. Let's not worry about that so much. Now you apply a very small drain voltage. So between the source and the drain there is a voltage that is applied, and that is going to affect the field across this part, and we assume that the field will now go, I mean there is a linear variation of the potential across this region. So the current will start flowing, it will behave like a resistor and the current will start flowing. Okay, this will start behaving like a resistor and the current will start flowing from the source and the drain slowly, because as you increase the drain voltage here, your field will increase here, and so the current that is flowing across this is also going to increase as you increase drain voltage. But remember, this is all when the gate is turned on at a voltage higher than the threshold voltage. If your gate is turned off, then all these things do not matter, everything is going to be 0. Okay, so you are applying a small drain voltage and you are slowly increasing the drain voltage, because this is a pure drift sort of a transport where basically your electron holes, when electrons here, of course it will be electrons here, electrons will experience a force which will basically accelerate them in proportion to the field that you are applying. So as you are increasing the drain voltage, your field here is increasing, so your current through the channel also, it's called ID, the drain current is the current through the channel here, the drain current also will keep increasing with the drain voltage. But so what I mean is that if I look at the, if I take the marker here, I mean if I take the, so what's going to happen is that if I am plotting the drain current is basically the current that goes here. Okay, the electrons that goes here, actually the electrons are going like that, so that is the drain current, the real current is coming this side, I mean that is the notion, but the electrons actually going this side, source to the channel that is formed to the drain, channel is already formed, so there is no issue with that. But as I am increasing the drain voltage, this is called, on the x axis I have drain voltage, so I am increasing the drain voltage from 0 to then 0.1, 0.2, 0.3, I am increasing the voltage. Your current, because this is a resistor, this behaves like a resistor. Okay, this behaves like a resistor, so the current will keep increasing, it will not indefinitely increase. By the way, what will happen is that there is something that will very interesting that will happen, I will come to that right now. Okay, so what will happen is that you see, when you apply when you keep applying a drain voltage which is higher and higher, what happens is that at gate you are applying some voltage, suppose the threshold voltage was 1 volt, so at the gate you are applying a little higher voltage, suppose you are applying 1.2 volt, so the channel is in strong inversion, so this is 1.2 volt that you are applying on the gate. Okay, here it's 1.2 volt, but see this drain you are applying a higher voltage, say 10 volt or 5 volt or whatever. So with respect to the drain here, okay, this is a small voltage, doesn't matter, this is a little large voltage, say 5 volt. With respect to the drain here, this gate actually will be pinched off. Why? Because if I take, this is 5 volt, this is 1.2 volt, this is 1.2 volt, okay, 1.2 volt, which is channel is on, and this is for example 5 volt. Instead of that, I can also say that this is at 0 volt and this is at minus 3.8 volt. The difference is still, the delta V is still 1.2 volt, right? No, this is 3. This thing volt, the same as the delta V is same as 5 volt minus 1.2 volt. Okay, it's the same difference, right? So what I am trying to say is that I can say that this is at 0 volt, this is at 0 volt, and the gate is at minus 3.8 volt, which means the gate is pinched off here with respect to the drain. Why am I saying that? The same thing that essentially I am telling you, right? If you listen carefully, this point if I apply at 5 volt and the gate is applied at 1.2 volt, okay, it means the difference between the gate and the drain is minus 3.8 volt. The delta that is there is minus 3.8 volt, and that minus 3.8 volt is happening here because the potential is varying linearly across this. Okay, so this point will have the extreme case where the difference between the potential here and the potential on drain is minus 3.8, which means this particular part is actually pinched off with respect to the drain. Okay, with respect to the drain it will be pinched off. You see my point, right? With respect to the drain it will be pinched off. So what will happen now? So what will happen now is that this point will get pinched off, which means the channel will basically almost be not there. I mean it's coming to 0, and you can see this profile, this channel, this is the channel actually profile, this triangular profile that looks like this, no, that looks like this is the triangular profile, this is actually the channel profile, this is the channel profile, and this channel profile means the electrons actually. So the electrons are highest here, electrons are gradually decreasing, eventually at this point electrons will be almost 0, it's called pinch off condition. It's not the channel pinch off, it's the pinch off at the drain edge of the gate. So this pinch off has happened, and this gradual variation of the triangular sort of thing, that means the channel is higher here, lower, 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 eventually even lower, lower, eventually the channel becomes 0 at this point, is because the potential Vx is linearly varying. The potential is linearly varying across from this point to this point. The potential is linearly varying because you are applying a drain bias here, some 5 volt or 10 volt or whatever, and this is 0 volt. So the potential is linearly varying, and that's why the shape of it is going like that. At one point here, the difference of potential between this drain and the gate is essentially such that the gate is pinched off with respect to the drain, so the channel is pinched off at that point. You see that point? That's written very carefully over there. Okay, that's written very carefully over there. Let me rub out here again. Okay, okay. So you see the channel is pinched off over here, and the moment the channel pinched off over here, the current will not increase any further. The current will basically saturate, sort of tend to saturate. So this point is called VD sat. That means it is the onset of saturation. Okay, till this point only you can go linearly with the resistor, this behaving like a resistor. At this point, some point here, there will be pinch off here, which will prevent the current from increasing any arbitrarily further anymore. And after this point, what will happen is that as you apply more and more drain bias beyond this point, as you apply more and more drain bias, the current will saturate like this. The current will saturate like this. Why? Because as you apply more and more drain bias after that, your depletion, this is your depletion, you see, this is your depletion. This depletion will increase. Okay, because applying more positive voltage here, the depletion will increase, and this pinch of voltage will move to the left. You will deplete more and it will move to the left. So what I am saying is that if you look at this next figure here, we will come to that figure over there. Okay, we will come to that figure over there again. Same thing as drawing here, actually is the same figure that has come here. This pinch off over here has now moved over to here. The pinch off has moved there. So now the depletion has also increased a lot. You see, compared to this, the depletion has increased a lot, and the pinch off has come over here because you are applying a more and more drain bias, so the pinch off keeps coming to the left. Okay, and this point and this point, this is a depleted region, and this behaves like a base collector junction of a BJT. If you recall, it's a very high field region that exists like a base collector reverse bias junction. So whatever electrons reach here at this point will be swept away, by the field from this point to this point. This is a huge field here. So whatever electrons reach this point, okay, and this point will be such that electron density will almost go to 0. Whatever electrons reach this point will be swept away by the field. Very strong field exists here to this side. Okay, and that is like a base collector depletion region, reverse depletion region, if you recall, is the same thing, almost the same thing. Okay, so how many electrons are arriving here matters, not with what speed they are being swept away by the field here. That's why the number of electrons arriving here will be constant, because this voltage will be maintained at this voltage. Okay, so that voltage will be maintained here, even if it goes here, it will be maintained here. So the number of electrons arriving here is the same, doesn't matter where the point is, so the current will be constant. How fast they are swept away by this huge field is not important, just like a base collector junction of a BJT. Okay, so essentially what we are going to get is that initially you will have a linear sort of a curve. The moment you have a pinch off here, you'll deviate from the linearity, and any more after that you apply, any more drain voltage you apply, your pinch off is gonna move to the left. Your pinch off is gonna move to the left here. Depletion will widen even more. Your pinch off has moved to the left, and how many carriers are reaching here actually matters as to how much of current you will get here. Remember, this entire region is a very high field region, like a base collector junction of a BJT, so it will sweep away very fast. That's why it will be saturated. There will be no, because at this point the number of electrons reaching is constant, and this correspond to different gate bias. So your gate bias, if you keep increasing the gate bias 2 volt, 4 volt, 6 volt and all, then you will get more and more current for the same drain voltage. Are you seeing my point? So basically this is the ID-VD characteristics. This is called the ID-VD characteristics of MOSFET. It's called output characteristics of the MOSFET, because you're looking at the output current and you're looking at the output voltage. This is the output current and this is the output voltage. Okay, so this is called ID-VD characteristics. And you see the different gate voltage. If you increase the gate voltage, your also channel increases. For a given, this particular current is saturated, which means the drain actually doesn't have an influence on this part. Only the gate will be able to modulate the charge. Okay, So, this is the basic working of the MOSFET, and what we will do is that we will wrap up our lecture here today. So, we have introduced the basic MOS transistor. I told you that it is a 3-terminal device, and we discussed about the basic working very qualitatively. No equation, no expressions have come, no maths have come till now, they will come later. So, we have understood the working of the MOS transistor, how it works, why the channel pinches off, and why the current saturates. So, that was what our class today was intended to be. What we will do in the next class is that we will take it forward. We will probably go through some of the maths, is very simple maths to explain the threshold voltage. It will be very similar to MOSFET, a MOS capacitor. We will derive some expression for threshold voltage. We will do some IDVD, and also get a little bit more into the different other characteristics like gate transfer characteristics like the drain current versus the gate voltage and so on. And we will also take help of some simple equations to derive this IDVD that I showed you just now. Okay, some simple equations to derive them, which will be helpful to you. Okay, that we shall do that in the next class. Okay, thank you.